Hello everyone, I'm Viraj Nadkarni, a second year PhD student at Princeton University. Today I'm going to present our work for Financial Cryptography Conference 2024 named ZeroSwap Data-Driven Optimal Market Makers for Decentralized Finance. This is joint work with Jiachen from Peking University, Ranvir, Sanjeev and Pramod from Princeton University. Our current work concerns the use of automated market makers on DeFi. Currently, the form that AMMs take in DeFi is the constant function market maker. They are basically a smart contract interacting with two agents, liquidity providers and traders. The liquidity providers provide liquidity to make trades, to satisfy the buy and sell trades that traders come up with. And the price that the trades are satisfied at is a function of the reserves as provided by the LPs. In particular, the price is basically the slope of the bonding curve that the constant function market maker operates on. At any point of time, the market maker is at an operating point on the curve, and at the operating point, the slope of the tangent tells you the price that an infinitesimal trade would execute at. Let us now assume that apart from the market maker itself, there is an external market that decides the price of a particular asset. Let's say the price of ETH against USD. Currently the price is equal to 1. Let's say it jumps to something like 4. Then, because of the external price change, arbitrageurs are prone to take advantage of this and buy the asset ETH from the constant function market maker and sell it on the external market. They would keep buying ETH until the slope of the tangent equals the external price, which is 4, and reach a new operating point 50 to 100 as shown in the figure. However, had they known the price in the external market and sold it at that price, they would have committed the second trade as shown here and ended up at the point 50,300, thus making a profit. However, the LP ends up executing the trade at a worse price than the market and hence suffers a loss. This signifies a need for an adaptive AMM. Since the external price keeps changing and the bonding curve is static, we see that every arbitrage trade is going to incur loss. This loss has been quantified previously as loss versus rebalancing and is proportional to price volatility. In order to capture this loss, we need to adapt the fees of the market maker to market conditions. Basically, we need to increase fees when the volatility increases and decrease when the volatility decreases. However, how are we supposed to do this systematically? This is the question that we seek to tackle in our work. To do that, we introduce a model for how traders behave. We want to incorporate how they would react to changing prices and changing external prices. To do that, we take the support of a model that has been used extensively in market microstructure literature, which is the Gloston-Milgram model. The external price process in the Gloston-Milgram model drives the trading behavior. We classify traders into two types, informed and uninformed. Firstly, we assume that time is divided into discrete chunks, and in each chunk, the hidden external price process, P external, follows a random walk with jump probability, sigma. And in each time step, the market maker quotes an ask and a bid price, PA and PB. Market maker buys the asset at the bid price and sells it at the ask price. Also, in each time step, the two types of traders arrived with varying probabilities. The informed traders arrived with probability alpha, and the uninformed arrived with probability 1 minus alpha. The trade action, dt, is a discrete number. It is either a buy trade or a sell trade respectively, +1 and -1. If the trader decides not to trade, then dt equals 0. we assume that the trade size for each trader is fixed. Basically, it's just a single unit of the asset that the trader decides to buy or sell at any point in time. The informed trader, as the name suggests, can see the external price. Therefore, it buys or sells only when it makes a profit. Therefore, it will buy when the external price is greater than ask, so that it can buy from the exchange and sell it on the external market, and sell if the external price is less than the bid, so that it can buy from the external market and sell it on the exchange. Meanwhile, the uninformed trader, as the name suggests, does not see the price and buys and sells randomly with probability half. With an aim of avoiding arbitrage loss, we define the goal of our agent as the following. We want to set the ask and bid prices so that the conditional expectation of the external market price, given the history of trades and trader actions and trader prices, is equal to the ask if the next expected trade is a buy, while the same conditional expectation should be equal to the bid if the next expected trade is a sell. The properties of these particular goals are as follows. Firstly, if we write the expected loss to arbitrage in the next time step, and we assume that the ask and bid prices have been set according to this goal, then it turns out that the expected loss is exactly 0. This means that we are balancing profitability of the market maker and while staying competitive, in the sense if the market maker decides to make a slight profit by either setting an ask price greater than the recommended one, or setting a bid price less than the recommended one, then another market maker can always take away our trade volume by setting ask and bid prices that are slightly less and slightly higher respectively, until you reach this the given condition. Thus, the two equations written here can be thought of as conditions for market efficiency for any AMM. Let us now see what happens if the market maker knows exactly the trader behavior model. That is, it knows the parameters sigma and alpha. In that case, we can use a Bayesian equation to update our ask and bid prices and get the optimal ask and bid recommendations. So we initialize a belief over prices, a belief probability mass function over prices as B0. Let's assume we know the initial price exactly. Then we set ask and bid prices by solving the following fixed point equations. Note that these equations are nothing but the conditions that we proposed in the goal for our market maker. The reason why we are calling these as fixed point equations is that on the left hand side we have the ask price, and on the right hand side the ask price also features because to evaluate this conditional expectation of the external price given a trade, you would have to use whether or not the external price is above or below the ask price. So this is basically a fixed point equation in the ask price. Similarly, the second equation is a fixed point equation in the bid price. In the third step, we observe the trader action dt after having set the ask and bid prices according to step 2. And in step 4, we update our beliefs according to Bayes' rule, and then we go back to step 2 to solve the fixed point equation and set a new value for the ask and bid prices. However, for more complicated price jump models, the equation specified in the goal can become intractable. This means that step 2 of the previous algorithm would be computationally very difficult to perform. More importantly, the variables alpha and sigma are unknowns in reality. Thus, we need a model-free algorithm to set prices. Thus, when the model parameters are unknown, we reformulate our problem as a POM-DP, or partially observable Markov decision process. This process is defined by the by these 6 variables. Firstly, the state contains the external price and the trader action at each point in time. The action contains the action done by the market making agent, which is the ask and bid prices. The observation is the part of the state that the agent can perceive, which is just the trader action. And the policy party sets the action, basically the ask and bid prices, according to the history of observations and history of actions. The state transition, meaning the way ST goes to ST plus 1, is specified as per the Coloston-Milgram model. So what remains to be seen is what should be the reward so that we elicit the desired behavior from our market making agent. Note that the goal of our market making agent is to track the external price without having actual access to it. Thus, the market making agent needs to infer the external price from the history of trades and ask and bid prices. The intuition behind designing the reward is as follows. Firstly, we want to penalize the agent for accumulating a large trade imbalance. That is historically a large number of buy or sell trades. Because what this means is that if on an average the market maker has been recommending an ask price that is below the external market, the market maker is going to accumulate a lot of buy trades. Conversely, if the market maker has been recommending the bid price as above the external price, then it will accumulate a lot of sell trades. We want neither of these things to happen, and this would imply we want to track the external price correctly by minimizing the trade imbalance. Also, because we want the market maker to remain competitive, we would like to penalize the agent for having a large spread. This makes the ask and bid prices closer to each other and thus more competitive. So we set the reward in each step as follows. The first 2 terms basically penalize the increase in imbalance. This encourages the agent to keep imbalance as close to 0 as possible, while the third term penalizes a large spread. This is again because imbalance measures the amount of net trade that happened in recent past, and this we calculate on a sliding window of, let's say, 20 to 50 trades, and set the imbalance for each time step equal to the net trade that happened in the last 20 time steps. Now we provide some intuition for the algorithm used when the market maker does not know the trader behavior model. We treat the imbalance, that is the sum of the trades in the recent past, as the state ST. We treat the change in the ask and bid prices as the action for the agent. We expect large imbalance to indicate the need to increase or decrease price in an appropriate direction. The goal of each agent is to estimate the expected future cumulative reward as defined here, and it needs to do that for each pair of state and action. If the estimation is done correctly, this gives us the best possible action for any state, which would be the argmax of this Q function over all actions. Once that action is taken, we would assume that the cumulative reward would be maximized, and indirectly we would have the competitive market maker condition to be satisfied as defined before. Next, when the algorithm is in state S, we choose random action with probability epsilon. This helps in better estimation of this Q function for different S and A values. This phase is called the exploration, and we choose an action that maximizes this Q function with probability 1 minus x epsilon, and we call this phase as the exploitation. This is a standard trick that is used in reinforcement learning or multi-arm bandit algorithms to maximize to balance between estimating a specific Q function and using the information that you already have to provide the best action. We then make epsilon decay with time so that it explores more at first to improve estimates and then exploits to make the market maker as efficient as possible. This algorithm is very similar to Q-learning that is used directly for Markov decision process. However, because we conjecture that the trades are linked to the hidden external price, we conjecture that this partially observable Markov decision process in this case would also lend itself to Q-learning. We now demonstrate the performance of our policy, and we highlight that it does not need any prior training and tracks the external price for each sample path that the price takes, as opposed to tracking it on an average. The RL policy also tolerates large jumps in prices. In the figure on top, we see the external price and the ask and bid prices as recommended by the RL algorithm. Initially, we see that there is a large deviation between these three, but eventually the algorithm learns to track the external price exactly, even though it doesn't have any access to the external price directly. The deviation from the mid price of the external price also decays to zero quite quickly, while the spread also on an average is the same value as you would expect from a Bayesian policy, which knows the parameters of the model, such as the price jump probability sigma and the informedness of the traders alpha. As seen here, the RL policy also manages to track the external price when there are large jumps. Again, the mid price deviation and the spread decay very quickly, and we see that the arbitrage loss because of a large jump is also avoided by the policy. Further, we observed that our policy is robust to changing market conditions. That is, if we change the price jump probability sigma or the trader informedness alpha with time, even though the parameters are completely unknown to it, it would keep track of the external price. This robustness can be demonstrated through these figures. In the top left, we have the market conditions of the external environment. We see that the volatility and informedness are behaving quite erratically. In spite of that, on the top right, we see that the ask and bid prices converge quite closely to the external price. The deviation of the mid price from the external price also decays, and the spread also approaches a reasonable value. Therefore, the way we can use the above algorithm in a CFMM is in 2 or 3 manners. Firstly, you can use it as to provide an adaptive bid and ask price for a fixed trade size. Either that, or we can, when the trade sizes are too small compared to the liquidity in the CFMM, the RL policy can adapt the price much quicker than the curve itself. Or we can parameterize the curve to have a variable price at any reserve value. The parameters can be controlled by the RL agent, rewarded as before. We now give details on how one can potentially implement such a model. For this, we would have 3 agents interacting with the blockchain, and this would be implemented similar to an optimistic rollup. Firstly, we have the traders, then we have the validators, and then we have the challengers. The first step is that the traders post trade request of buying and selling an asset. Second, the trade requests are collected by the validators. Third, they post solutions, meaning they post changes to the protocol parameters in form of changes to the Q table and the ask and bid prices. 4, they execute all of these buy and sell trades optimistically, assuming they are valid. Then the challengers check the validity of the solution, meaning if they check if the solutions delta Q, delta PA and delta PB are correct. They post challenges for an invalid solution. This challenge posting is made especially easy because although finding the argmax over all possible actions in a Q table is difficult, verifying whether or not the posted posted changes in the Q table deviate from their optimal values is relatively easy. After that, the contract verifies if the challenge is valid and slashes the validator if it is so. We can generalize the algorithm to any trade size and variable trade size. This would entail recommending an entire bonding curve after each trade. And since an informed trader in this case is allowed to arbitrage as much as their belief is, the Markov decision or the partial Markov decision process reduces to a filtering problem. So in this case, for known price statistics, for known price statistics about the jump in the price and the informedness of the traders, we can use Kalman filter to recommend the curve. In the case of unknown price statistics, we use Kalman filter with the expectation maximization algorithm, or in other words, an adaptive Kalman filter to do the job. Using these kind of Kalman filter based AMMs gives us a much better and dynamic curve, and which in turn gives us much better and efficient prices and drives down the monetary loss to arbitrage and thus loss versus rebalancing. In conclusion, we saw an example for the need of data-driven adaptive methods in decentralized finance and observed that the blockchains make this problem sequential, and because of the nature of needing adaptivity, data-driven behavior and sequential decision making, we turn to reinforcement learning. We observed that reinforcement learning policies are not only efficient in the market making sense, but also robust to changing market conditions, and they in general avoid arbitrage loss and are more market efficient in the specific way we had defined.